So this is on the mole. The mole is an SI unit. That means internet is an international standard, and it is used to quantify matter. If you say you have 1 mole of something, that's twice as much as half a mole. If you have 2 moles, that's twice more. To do mole problems, or most of the math in chemistry, requires a good, solid understanding of how to utilize factor label method to solve problems. It's also helpful because that's how the text does all the work. So if you want to read the text or read a review book, that's what they're using. And if you don't understand the method, you're not going to be able to use resources. Now, traditionally, factor label method is used for proportional relationships. So, let's say you have 10 yards, and so you have 10.00 yards, and you want to know how many centimeters that is. And you have some fun facts here. You have that 1 yard is 3 feet, 1 foot is 12 inches, and 1 inch is 2.54 centimeters. Now, I'm figuring most of you could figure this out in a couple of seconds and use your calculator and get the answer, but if you're taking an exam and you have to justify your answer, you're going to have to show your math. So I'm going to show you the math, and I'm going to show you how the factor method actually takes up less space, and it's exactly the same thing as using proportions, and then I'm going to use that later on when I do some questions on the next page or slide of this video. So suppose the first step will be to set up a proportion. For every 10 yards, 10 yards is to x, as 1 yard is to 3 feet. And then we would cross multiply. So we move our x up here, we move our 1 yard down there, we move our 3 feet over here, and we'd end up with a situation like this. We'd have 10 yards times 3 feet over 1 yard is equal to x, and we could solve for that, and obviously the answer is going to be 30. The factor label method does sort of the same thing. It takes this fact and turns it into a factor by which we're going to multiply our original number. Now watch the setup, because what we end up with is this. That this is this. So we end up with 1 yard. Notice now the yards are going to cancel each other out, aren't they? And on the top we have 3 feet. Now at the end of this, we're just basically multiplying 10 times 3, which we all know is 30 feet. However, if we're doing it by this method up here, we're going to have to set up another proportion and another proportion to show it. It takes up a lot of space. So to save ink, and just because it really is more efficient, we just do the next step. We put another parentheses here, and we go, all right, let's use fun fact number 2. We'll pick this one. 1 foot is 12 inches. Now notice we're just multiplying 10 times 3 times 12, but the feet are going to cancel each other out, and now we're in inches. And now we can do the last step. We put our 1 inch on the bottom and our 2.54 centimeters on the top, because we want our answer in the numerator. We don't want to answer in the denominator. There's no point in that. We want something over 1, because everything's over 1. And then we just multiply that out, and we get 9, 14.4, and because all the other units cancel out, our answer is in centimeters. And by the way, fun fact, this has 4 sig figs. Everything in here is an exact number, including this is the only exact relationship in the metric system, which means we hold on to the 4 significant figures and the 1 measurement, because the things in the brackets in this case have no impact on the outcome or result of our calculation. So that is the correct number. That's the correct answer for the number of centimeters. Next page. All right, so what is the mole? The mole is 6.02214 times 10 to the 23rd of anything. You could have a mole of pennies, you could have a mole of marshmallows, or you could have a mole of atoms or a mole of molecules. And that's why a mole of something can have a different weight depending on what it is. If I had 6 times 10 to the 23rd marshmallows, it's going to weigh a hell of a lot more than 6 times 10 to the 23rd atoms of helium. However, there's a reason why we use this unit, why it's been devised, and why it's so helpful and useful. And it really has to do with this little fun fact down here. I'm using fun fact a lot for some reason today. And that is that 1 AMU, that's the unit that we used in average atomic mass, is equal to 1.6605 times 10 to the minus 24th grams. And to illustrate this, let's use our standard for measurement of atomic mass units, which is the carbon-12 atom. And let's find out what a mole of carbon atoms would weigh. So we're going to do this by factor label. So let's say we have 6.02 times 10 to the 23rd atoms of carbon. And we want to know what that weighs in AMUs first, but then we want to convert that into grams. So what we would do is we would set up, the first thing we would do is we try to convert from, try to get our mass in AMUs first, because we know that one atom of carbon, notice how carefully I'm labeling this, so atoms of C weighs 12.011 AMU. And that's on your reference table. Now, if we do this math and we multiply this out, we will get a really, really large number, of AMUs. But if we want to convert that to grams, that's going to do something. Watch what happens here. If I want to convert that to grams, I use the fact that 1 AMU is 1.6605 times 10 to the minus 24th grams. A couple of fun, interesting, useful things to notice here. This has 5 sig figs, as does this number right here. Okay, these are rounded numbers, all of them, by the way. Okay, so you have to use these when you want to do sig figs. Second thing you want to notice is the AMUs cancel out. We're going to get things in grams. Third thing you want to notice is this 10 to the 24th right here is going to really sort of counteract that 10 to the 23rd. All right. So what happens when you multiply this thing out? Well, you get exactly 12.011 grams, or close to that when you round it. Now what's important to know is this. This is always a mole. This never changes in the calculation. And this fact here never changes either. It's a fact that 1 AMU is 1.6605 times 10 to the minus 24th grams. So therefore, if let's say you had something else, let's say you had some oxygen, right, O2. O2 has a formula mass of 32.00 AMUs. If you were to stick this number up into here, the rest of the calculation would remain the same. Therefore, when you stuck that number in there, your answer would not be 12.011, it would be 32.00 grams. In other words, okay, and this number right here is what we call the molar mass. It's also called the GFM, or the gram formula mass. Those terms are used interchangeably. It's basically the mass of 1 mole of a substance. Now, the substance could be made of one atom like carbon, or it can be made of molecules of oxygen. But 1 mole of oxygen weighs 32 grams. 1 mole of carbon weighs 12 grams. And it varies. So if I had a mole of carbon dioxide, I would look up the C, right? And I find the C is 12.011. I have my 2 oxygens, which weigh 32.00. Now this is all in AMUs. So if I add these together, I get 44.01 AMUs. Now that's the mass of a single molecule of carbon dioxide. How much would a mole of carbon dioxide weigh? Well, we could set up the whole thing again, but it's not worth it, because we would do the exact same thing. We'd be like, okay, if I 6 times 10 to the 23rd, I'm not going to write out atoms, molecules, okay, of CO2, and if 1 molecule weighs 44.01 AMUs, molecules of CO2 cancel out, and then I do it one more time. Well, how much does that weigh in grams? I go 1 AMU is 1.6605 times 10 to the minus 24th. Well, guess what? These numbers are the same. My answer is 44.01 grams. That is the gram formula mass, and that's what a mole of CO2 weighs. So I'm going to stop here and put this up as a single video, and then what I'm going to do is I'm going to put up a second video in which I sort of try to get you comfortable with the mole as a concept. And we will call that mole 2.